Alright, so what I want to do today is I want to continue with our work on complex mappings. So there's a whole slew of examples we can do. I've got a bunch from the book that I thought we would just go through quickly. So the more examples you look at, the more you can build up your intuition. So the first is we take the upper half plane, which was denoted by H, and we have the following map. F of z is z to the alpha. And I'm claiming it sends it to this region over here. So what can you tell me about alpha if this is what happens? So I'm somehow taking this and I'm compressing it into this angle. What do you think alpha would be? So I've got, an r e to the I theta. I'm going to r to the alpha, e to the I theta over alpha. At least if alpha is real. So what should be true about alpha for this picture to be correct? 1/4, something like that. So this is probably alpha less than 1 and greater than 0. It's basically going to shrink the angle, and it's going to shrink the radius. Now since we're going all the way off to infinity, we're still going to have the entire sector. But it's going to map the whole upper half plane into a smaller piece. And another really good one is we take half the unit disk, and we map it to the upper right quadrant with the function f of z is 1 plus z over 1 minus z.
With the first function, should it not send r to the e I theta to r?
Oh, sorry, yes, you're right. Thank you. To the I theta alpha, yes, thank you. What about this function? So we claim that this is sending the upper half circle to the upper right quadrant. So how would you try to analyze something like this? So when you have an expression like this, how would you try to understand what's going on?
Make the denominator real.
Yeah, make the denominator real. Rationalize it. All that stuff from, I think, Algebra 1 all those years ago. We have 1 plus z over 1 minus z times 1 minus z bar over 1 minus z bar. Now when we multiply it, the denominator becomes 1 minus z plus z bar. So we get 1 minus 2 real parts of z. Plus the length of z squared. And then the top, is this how we want to do it? Yeah, because z plus z bar is going to just be twice the real part. And then up top we'll have 1 plus z minus z bar. So what's z minus z bar?
2 times the imaginary.
2 times the imaginary part of z. We have to make sure we remember the I. And then we'll have a plus length of z squared. So when we look at this, the denominator here is clearly going to be a real number. We would love it if this number is positive. Because if it's positive, we can then just read things off. This looks a lot like 1 minus the absolute value of z squared. But we're not quite subtracting as much as the absolute value of z, we're trimming it a little bit. So the denominator will be positive. So because the denominator is going to be positive, we can just read off the real part here. It's 1 plus z bar squared, that's going to be a positive number. And 2 imaginary part of z, well, the imaginary part of z is positive. So this is going to be in the upper half plane. And in fact, it's going to be in the upper right quadrant. So this is not a proof that this map works. as claimed, but it's at least strongly indicative. Okay, so I'll let you do the rest of the calculation, but I want to give you a sense of how you start doing some of these calculations, how you start getting a feel for what the maps do. And the big part is that this is positive compare to 1 minus the absolute value of z squared. And then we can just read things off. Okay, there's a huge number of additional maps we can look at. I'm not going to go through all of them. There's a lot of them going back and forth. The idea is, once you have a bunch of these maps, you can keep translating back and forth, you can keep combining back and forth. What's a really good set to know how to map into? I'll take 2 answers. Yes?
The unit disk.
Unit disk, and the other one? There's 2 ones we really like. We like the unit disk and we like one other one. It is one of the ones on the board. Yeah, the upper half plane. These are the 2 go-to regions. And frequently we'll do things for one, not the other, and we'll go back and forth between them. Okay, what we want to do now is we want to start proving properties of these nice isomorphisms between these different regions. We're going to use a lot of the results we've been doing throughout the semester. So the first result is, I think, just some kind of property about these maps. Yes. And so we have the following proposition. F is going to be holomorphic from U to V. It'll be injective. I think I also want to assume bijective. I guess it just says holomorphic and injective. Then F prime is never 0, and F inverse is also holomorphic. So these will be open sets, and for our purposes we can even assume simply connected. So here's our U, here's our V. And we have some map F between them. We want to show that F prime is never 0, and F inverse is holomorphic. Well, what can you tell me about the map F composed with F inverse? F composed with F inverse.
The identity.
It's the identity map. You could be even a little bit more specific if you want. Which identity map is it? Where does this identity map live?
It's from V to V.
It's from V to V. So I put identity of V. That way I can just quickly glance down and see where things live.
So we assuming that F is also onto.
Yeah. So for some of this, I think what we'll do here is, let's take V to be F of U. Let's make this restriction so that we are onto. We will need that if we're going to talk about, if we want this to be the identity. Is F of U going to be open? Do we need any conditions on F to ensure that this is open? We need one minor condition. What's the one condition we need on F to make sure that the, yes?
Non-constant.
F non-constant. F non-constant. So as we're going through the subject, we can start to see what we want to assume. If we're going to talk about maps from one set to another, we really don't want to take F to be a constant function. Remember, the identity function is not the constant function. It just assigns the input as the output. So we'll look at non-constant functions. We'll have maps from U to V. We look at F composed with F inverse. If we were to try to take the derivative formally using the chain rule, what would we get? We would get F prime at F inverse of Z times F inverse prime of z equals 1. So f inverse prime of z would be 1 over f prime of f inverse z. We can justify all this by taking limits and doing it formally through limits. Now you can begin to see why the proposition has as the first step that f prime is never 0, if we want to prove that f inverse is holomorphic. How are we getting f inverse's derivative? Well, we need a 1 over f prime. And we want to make sure that f prime is never 0. So the first part is going to be the crucial ingredient in proving the second. Before we go through the proof, it might be worth going back and considering the real case. Do we expect the same result to hold in real variables? So let's try to build some intuition. So this is something the book is not doing. This is the value added for coming to class, or at least watching the video. What would be the analog of the unit disk if we were in real analysis?
The unit interval?
The unit interval.
Kind of more so? Negative 1 to 1?
Yeah, I would go negative 1 to 1. I would say negative 1 to 1. And let's have a map from negative 1 to 1 to itself. And let's consider the function f of x is x cubed. So I'm hoping my plotting skills are not horrible. I should be able to do one dimension. It should look something like this. And the value here is, and the value here is. So does this map negative 1, 1 to negative 1, 1? Is it injective? Also known as 1 to 1. Excellent. Is it onto? Is f prime of x never 0?
It is 0.
It is 0. Fails violently. F prime of 0 is 0. Not only is f prime of 0 0, we even have f double prime of 0 is 0. The real case is very different once again from what's going on in the complex case. We can't have a nice isomorphism, differentiable, infinitely differentiable. Is there an inverse function? What would be the inverse function here? I'm sorry? Yeah, the cube root would be x to the 1/3. This is differentiable everywhere but 0. And at 0, if you try to take the derivative, 1/3 x to the negative 2/3. It's going to blow up there. Not differentiable at 0. So again, whenever you have a resultant complex, always go back and look and see what is going on in real variables. And if the result is different, we need to use something fundamental about complex functions that is not present in the real case. So something is going on here. Our functions have special properties if they're complex holomorphic. There must be something that we can then use to get the result that f prime is not 0. Okay? So the question is going to be, what will be our result? Proof that f prime is not 0. So what do we know in complex about our function that we do not know before? In both cases, we had differentiable functions. What else do we know in the complex case? So what's special about a complex function that's differentiable that's not true about a real function that's differentiable? Hopefully we've got some properties. What do we know? So analytic. So good. We know f is analytic. So we can write f of z equals maybe f of z naught plus f prime of z naught, z minus z naught, plus yada yada yada. Without loss of generality, let's assume z naught is 0 and f of z naught is, just to make life easy, 0. We might as well, I mean, all this is doing is this is just translating the whole set by sliding z, and then we're subtracting a constant from the function. If we subtract a constant from the function, we don't change whether or not the first derivative vanishes. So we can simplify notation. We can assume z naught is 0. We can assume f of z naught is 0, right? And we can assume that the first derivative vanishes at z at this point. And for a contradiction, assume f prime of 0 is 0. So therefore, we have the setting f of z is equal to an z to the n plus, say, g of z. N is greater than or equal to 2. G of z is going to be an plus 1, z to the n plus 1, plus dot 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 dot. Okay? So we have to have some expansion like this, where n is greater than or equal to 2. And we want to prove that this can't happen. Now we have the assumption that f is injective, so different things get sent to different places. Seems like that's got to be something we want to use to get a contradiction. What would be the easiest case to understand for G? What would be the easiest G to understand?
0.
0. So imagine G is 0. So then we have f of z equals an z to the n, where n is at least 2. Is this going to be 1 to 1? Or would we have different z's giving us the same output? So let's assume G is 0. Assume G of z is 0. If we can't even do this case, we're dead. Let's see if we can do that. So then we would have, say, f of z equals an z to the n. We want to violate injectivity. We want to find 2 points that get mapped to the same. Can you give me 2 different z's that get mapped to the same thing? So I claim, say, w, and what should I multiply w by to get the same output?
If n is even, we can take minus w.
So if n is even, we can take minus w. More generally, what could we do for any n?
E to the I, 2 pi over n.
E to the 2 pi I over n. So these ones would both get mapped to the same thing. So this violates injectivity. It's just faster to write 1 to 1. Yes?
How do we know that the e to the 2 pi I over n is also in our set?
No, it's w and w times this. These two numbers have the same absolute value. I'm just taking a w very close to 0. So these are close to 0. Remember, we're doing our Taylor series expansion about the point 0. So if w is really small, because we have U as an open set, there's a small disk containing 0 that the map is defined on. Okay, I've got to somehow justify my existence. Why does this work here and give us a contradiction, but it doesn't work in real variables? I mean, in real variables, things blow up. What's the difference?
E to the 2 pi over n.
I'm sorry?
We can't do that over here necessarily, unless.
We can't necessarily do that. So if we had n equals 3 over here, right? Let's try to take the cube root of e to the 2 pi I over 3. We're not going to get a real number back. You always want to go deep and see why is there a difference. What's the failure here? And the failure here is e to the 2 pi I over 3 is not in R. But it is in C. And so we're okay with our small little neighborhood there. We have more freedom. Okay, so hopefully this gives you a clue now of what you can try to do. So again, I realize I am going through this proof a lot slower than I need to. We can blow through this as they do in the book. But I really want to highlight how you think about these problems, how you attack them, how you approach them, how you come to this. We know that there's a difference in behavior between here and in the real case. There's got to be something that's explaining that difference. Where is this difference coming from? Well, one of the big things we know is f is analytic. Well, you know, the counterexample we have from real analysis, is that an analytic function? Yes! X cubed is analytic. So it can't just be that there's a series expansion. It's got to be deeper than that. But it is a property coming from a series expansion. Alright, so now this was the special case when g is 0. In general, g is not going to be 0. Oh well. But does this remind you of anything? We have a function, and then a function plus a small pollution. Whose theorem? So we've got a function, and we're adding a little bit to it. And we want to count how the number of solutions to an equation varies. Whose theorem is this? You're nodding, so.
I don't remember the name, but I remember the theorem.
Some dead person's theorem, right? Rouchet, right? Rouchet's theorem. Rouchet's theorem says if you have two functions, and your one function doesn't vanish on your boundary, and the other one is smaller in absolute value at each point than your function, then they have the same number of zeros in the interior. Well, because g has an extra factor of z, if you are sufficiently small, this extra z is going to make g of z much, much smaller than a and z to the n in absolute value. So these two functions will have the same number of zeros in a small disk. How many zeros if we take a and z to the n equal a specific value? That will have n roots. So that means this function will have n roots. And that will be the contradiction. So, small enough z, circle of radius r, have the absolute value of g of z is strictly less than a n z to the n. So, by Rouchet, f of z, which is a n z to the n plus g of z, and a n z to the n have same number of roots inside circle. And how many roots is that? What can you tell me about the number of roots? Number of roots is how much? How many roots does a and z to the n have inside that circle? N, which is greater than or equal to 2, contradicts that it's 1 to 1. So that's the proof. It's a nice application of Rouchet's theorem. It's one of the big differences we have between complex analytic functions and real analytic functions. We have this beautiful way of seeing how the zeros, the count of zeros change as we deform our function. If you look at real variables, if I change my function just a little bit, could I change greatly how many real zeros it has? Yeah, think of the parabola, y equals x squared. It has a double root at 0. If I look at x squared minus epsilon, where epsilon is positive, I now still have 2 roots that are very close to 0. But if I look at x squared plus epsilon, it will have no real roots. And so the number of zeros, x squared plus epsilon no real roots, x squared, 2 real roots, x squared minus epsilon, 2 real roots. The number of real roots will drastically change. Now, the number of complex roots will not drastically change. But there are issues when you restrict. Okay, so this is a really important property of these nice holomorphic maps from our open set to the image. Because really, if we're going to look at f from u to v, we might as well just restrict our output to v equals f of u. We know f of u is going to be open, that's going to be the points that are hit, that's the part we should be really looking at. In the earlier problem, which I've erased, which I think was about this part of the blackboard, when we mapped the upper half disk to the quarter plane, we could have considered it as a map to the upper half plane, just not hitting a huge amount of the upper half plane. Well, it's sometimes easier to just restrict yourself and look at just the part that's hit. You remember years ago the differences in terminology between the range and the domain? And it just makes sense a lot of times to just restrict yourself and say, I'm going to consider my output space to just be the set of points that I hit. Okay, any other questions about this? Alright, I want to now move on to the Schwartz lemma. How many of you have seen Spaceballs? Not nearly enough. Alright. What's the best line in Spaceballs? All the good lines. I guess best line you can say in public. Or at least if we're going to prove something about the Schwartz lemma, I think it should be obvious what we want to assume right now. Alright. So one of the problems is there's two Schwartzes, just like the movie. This is the one with the Z. Alright, so the Schwartz lemma. So we're going to have, we just want to make sure we get all the conditions right. F is going to be a map from D to D, the unit disk to the unit disk is going to be holomorphic. And we might as well normalize so that f of 0 is 0. Do we know any way to take a map from the unit disk to the unit disk and compose it with something to make sure 0 gets sent to 0? Yes. We just learned how to do that with those maps C alpha last time. So if you weren't being sent to 0, first compose it with something like this so that now you're good. Right. Then the following things are true. The first one is that the absolute value of f of z is thus equal to the value of f of z. The second is if there exists a z0 such that f of z0 in absolute value equals the absolute value of z0, then f is a rotation. And the last is, I think, the absolute value. Yes, is f prime of 0 in absolute value is less than or equal to 1, and if equals 1, it is a rotation. So what's going to be useful about this, again, is it's going to allow us to classify maps. What we're leading up to is a complete classification of the automorphisms of the unit disk. If we can understand the automorphisms of the unit disk, do we understand the automorphisms of the upper half plane? Yeah, this is one of the things we did last time, is we said, well look, if we understand one space, and we understand a map from that space to another, then we can pass back and forth between the automorphism groups. So if we can understand what's going on in the unit disk, we understand what's going on in the upper half plane. Depending on how you're doing number theory, and that's really what you should be doing, you will want to work either in the upper half plane or in the unit disk. What this tells you is that if you understand what's going on in one space, you understand what's going on in another. We're leading up to a generalization of continuous functions that are periodic. Now for us, of course, continuous is too weak. We might want the functions to be differentiable. On the real axis, there's really not that many transformations we look at. We normally look at translations by, say, a positive integer. This is your Fourier series. We're building up to modular forms, to generalizations of functions that transform nicely under a large class of transformations. Or maybe they're not exactly identical, maybe there's a small conversion factor for each transformation. So maybe it's not quite periodic, but maybe it's almost periodic in some kind of nice, easily controlled factor. And if we can understand what's going on in a certain region, by understanding how it transforms, we can understand it elsewhere. Alright, so it's time to prove them. So prove. So let's do one. So let's consider g of z equals f of z over z. So what's your first concern as soon as I do this?
What about z equals 0?
What about z equals 0? Chill, relax. So, come on. So why am I not too concerned about z equals 0?
Because you said f of z to be 0.
Yeah, we said f of 0 to be 0, so we have a removable singularity. But you're absolutely right that we should be concerned about what's going on at 0. We also have f of z has a Taylor series expansion at 0. We know it's going to start off with at least a z to the first power. Right? Okay. So we know g of z equals f of z over z is holomorphic. Thus, g is holomorphic. What do we know about holomorphic functions? We're trying to show something f of z is less than or equal to absolute value of z. There's another way of writing this, i.e. f of z over z is less than or equal to 1. We're talking now about a ratio. We're talking about the magnitude of this function g. Do you know anything about where holomorphic functions are large?
On the boundary?
On the boundary. So consider a circle of radius r less than 1 about origin. Then f of z over z, which is g of z, attains max on boundary. So again, this is something that's very different than the real case. You can have many real valued functions that are continuous and infinitely differentiable that are not taking on their maximum value at the boundary. Look at something like 1 over 1 plus x squared. How large is f of z? Do you know anything about how large f of z can be?
Less than or equal to r.
We don't know f of z is less than or equal to r. All we know is f maps the disk to the unit disk to the unit disk.
Okay, yeah, sorry, I was taking the first one as an assumption.
Right. So what do we know if it maps the disk to the disk? How large can f of z be in absolute value?
Less than 1.
Less than or equal to 1. Probably strictly less than 1 if it's mapping the disk to the disk. So as f of z is in D, that implies the absolute value of f of z is less than or equal to 1. And so if the boundary is where the maximum occurs, then we know f of z over z is less than or equal to 1 over r. And this is true for all r less than 1. So what do we do? So for any value of r less than 1, this is true. We send r to 1. So not to 1. Sorry. So if we send it to 1, then we get f of z over z is less than or equal to 1, so f of z is less than or equal to z. And that will give us f of z is less than or equal to z. If this weren't the case, then there would be some r where we would have a contradiction. Let's say f of z was greater than 0.9999999c, 0.9999999z. Then if we take r to be so close to 1, we would get a contradiction. So the only way this can hold is in the limit as r goes to 1, f of z over z has to be less than or equal to 1, so we get f of z is less than or equal to z. That proves the first condition. Okay. Any questions about 1? I have an alternate proof. Do you want to do an alternate proof? Okay. So let's try to think about the second one. What would happen if there was a z such that f of z equaled z naught? So now consider 2. Assume there exists a z naught such that f of z naught equals z naught in absolute value. Yes.
Do we need that it's not 0 since we're given that?
Yes. Yeah, we should say it's not 0. Okay, yes. So we wanted, it's my favorite math thing to say, z naught naught naught. Right? With z naught naught naught. Okay? What would it, yes?
We can write z, f of z as some sort of rotation times z0.
Why?
Because they're the same magnitude.
At that point,
Yeah.
we can write f of z naught as a rotation of z naught, but we want to show that that rotation holds everywhere. So let's think back to a function g of z. G of z is f of z over z. And what do we know about this? We know it's less than or equal to 1. But we now know g of z naught equals 1. Ooh. Okay, so here's our unit disk. Here's our point z naught. The maximum of g has to be on the boundary. The maximum of g is not on the boundary. It's attained interiorly. There's only one way g can attain its maximum in the interior. G's constant. G constant by max modulus. So we're getting a lot of dividends now for those results, the maximum modulus, the open mapping theorem, the Boucher theorem. What can you tell me about that constant? Could it be 1701, one of my favorite constants? No. What can you tell me about the constant? Well, if the absolute value of g is 1, the constant has to be of the form e to the I theta. As the absolute value of g of z naught equals 1, that implies g of z equals e to the I theta. Well, if g is just f over z, then that gives you f of z is e to the I theta times z, therefore f is a rotation. That's nice. The only way we can have f of z having the same value is if it's a rotation. This is, some sense, if you want to try to think of what the map is doing, if you start off a fixed distance from the origin, you can't end up that distance from the origin. You have to either be pulled closer or pulled further away. The last one, the f prime of 0, we're saying that that has to be less than or equal to 1. So, proof of 3 that f prime of 0 is less than or equal to 1. Alright, so how would we try to go about proving that f prime of 0 is greater than 1? I mean, sorry, it is less than or equal to 1. Yes.
Could we use like a mean value theorem or something? Just try to show that it would get too big.
Okay, so we don't quite have a mean value theorem in complex. It's not a bad thing to try. I I mean, a mean value is in some sense a poor person's table. So, what are the thoughts? What do we have? Do you expect that this is true in the real case? Well, if you look at our map, you say from -1, 1 to -1, 1, the x cubed, its derivative is 0, so that's not a counterexample. So we'll return to this later if there's time. We've got about 10 minutes left. We should have time for that. So do people want to try to prove this now? Do people want to go and try to explore the real case and see what's going on in the real case? What do you want to do?
I'd rather prove this first.
Alright, I'd rather prove this first. What kind of things can we use to prove this?
This G of Z has been pretty handy so far.
So G of Z has been pretty handy before. Okay, so we could look at G of Z. Well, we know f of 0 is 0. So this could be written as a1 plus a2z plus a3z squared plus dot 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 dot. Could a1 be 0? Possibly. We're not saying we have an isomorphism from D to D. We're just saying we have a mapping from D to D. We could take, f of z to be z to the n. If we take it to be z to the n, no z naught other than 0 will be sent to something with the same absolute value. We could take it to be 2015 times z, and just compactify the circle. We could do that. So we don't necessarily know anything directly about A1. So all we have is we have an open map from disk to disk. And so I've got two different proofs of this. What would happen if A1 was greater than 1? An absolute value. So we have two ways of approaching this, right? We either show A1 is less than or equal to 1 in absolute value, or we show that if it's greater than 1 in absolute value, there's a contradiction.
Contradicts number 1, I think.
Yeah, contradicts number 1 very quickly.
Yeah.
If the absolute value of A1 is greater than 0, for z sufficiently small, let's say A1 is greater than 1 plus epsilon. We have the absolute value of A2z plus A3z squared plus dot 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 should be less than or equal to epsilon over 2. Why? Because this is going to go to 0 as z goes to 0. So if A1 is greater than 1 in absolute value, it's going to be at least 1 plus epsilon in absolute value. If z is really small, the best we could do is have this provide a negative epsilon over 2, canceling the epsilon a little bit, and this would yield g of z in absolute value is greater than or equal to 1 plus epsilon over 2 for z small. And this contradicts 1. I'm not going to go through the proof of the rotation. I'll leave that to you. I want to make sure we have time to talk about the real case. If this is equal to 1 in absolute value, the hope is that we could probably find some choice of z maybe to align this in that same direction and push us up a little bit, which would be a contradiction. So that there can't be any other terms here. That we should be able to align things somehow. So I'll leave that as an exercise for you to see if you can make that argument work. So do we agree with the Schwartz lemma? That f of z is less equal to z in absolute value if there's a z naught such that they have the same absolute value other than 0, then if there's a rotation, and the first derivative at 0 is less equal to 1. This is going to be extremely useful in terms of classifying things later. The first derivative can't be too large. What we want to do is we want to try to consider analogs of this in one dimension. So do you think these are true in the real case? What do you think? Is f of z less equal to z? So we're going to have, let's say, a map from negative 1, 1 to negative 1, 1. Yes.
Seems like there's kind of only one function in the real case that satisfies all this stuff.
Which is?
The identity map.
So the identity map works. Now what if we take the function cubing? Will this always hold if we take the cubing? So if we look at f of x is x cubed, yeah, that will still hold. So it's not immediately clear that this fails in the real case. The hope is that maybe we can somehow tweak things a little bit. And this should hopefully be some way to get 1 to fail. The one I'm more interested in is 3. I want a map, and I want f prime of 0 to be greater than 1. Anybody know a good function that maps negative 1 to 1 to negative 1 to 1? So we want an odd function that's 0 at 0. Right? I want you to come up with natural ways of finding these. I want an odd function. What was the suggestion?
Appropriately scaled sign.
Appropriately scaled, I love it. Appropriately scaled sign. What would be appropriately scaled sign?
Pi times
I'm sorry?
pi x.
So we want sine of pi x. So now when we put in x equals 1, we get 0. So this is not the appropriately scaled sign. It's close. How do we tweak it?
2x.
Pi over 2. So, very close. Excellent. Do we agree that this is a one-to-one function? Do we agree it's onto? Let's calculate f prime of x. So we get pi halves sine, I'm sorry, the sine is cosine pi halves x. What's f prime of 0? Pi over 2. And what can you tell me about the number pi over 2?
Bigger than 1.
It is bigger than 1. Exercise, prove that. It's not as easy as you think, Can you prove that, pi is greater than 2? If you go back to, geometry and circumscribing and inscribing polygons inside circles, you should be able, within a reasonable amount of time, to prove that pi exceeds 2. I don't need great bounds like, it's greater than 3. Just something weak that it's greater than 2. So what this tells you is, yet again, the real case is different than the complex case. So this should suggest a question. What question does this suggest? And the question was actually answered the first time I taught complex. So we've just shown f prime of 0 does not have to be less than or equal to 1. It can be as large as pi over 2. I want you to get into the mode of grad school. I want you to get into the mode of researcher.
Okay.
When you see something, think of a generalization, think of an extension, think of a question to ask. What question should we ask?
Can that prime of 0 be as big as we want?
Can it be as big as you want? How bad is the real case versus the complex case? Do you think that this can become arbitrarily large? Or do you think there's a universal constant, which we'll call the Williams constant, that says that no matter what isomorphism you have from -1, 1 to -1, 1, the first derivative can never be larger than the Williams constant?
You could keep nesting these signs and get an arbitrarily large one.
Ah, so could we keep nesting the signs to get an arbitrarily large one? Well, I would have to check and do the calculation to see that it's going to continue to work and still be.
We could just take a really steep line, really close to origin, and then smooth it at the ends.
Okay. So one question, of course, is I want to make sure maybe things are infinitely differentiable, just to be fair. Now, nesting signs looks like that's going to work. So as an exercise, see how, for extra credit, see how far you can push this. Can you get something arbitrarily large? And the answer is yes. And so you can make the first derivative as big as you want and still have an infinitely differentiable function. Can we have the derivative plus infinity?
Yeah. X to the 1/3.
I'm sorry?
X to the 1/3.
But I want it to be infinitely differentiable.
Oh yeah, that's a problem.
That's a problem. So there's a limit to how far I can, I can ask you to push this. But I can't ask you to push it all the way up to arbitrarily large constants. So that's a good place to stop today. Okay. So again, the goal of a lot of what we would